Welcome back. We're even the last days of final exam. I keep homework 3 is due tomorrow by midnight for the programming part, and everything we're covering from now on and is on. We already covered. The topic for today and probably next couple of days is dynamic programming. Dynamic programming is a general technique used for and the motivation here is that we've seen a lot of divide and conquer kind of strategy algorithms, but binary search is also divide and conquer strategy, and a couple of the graph algorithms that we looked at are also kind of divide and conquer. You're reducing. But as you might have seen before with a few examples that we're going to look at here, it can lead to very inefficient solutions. First of all, if you're actually going to one. Next number in the sequence, one previous to it, the one prior, so the second previous to it. So the next one, of course, would be 1 plus 2, so 3. Then the next one would be 2 plus 3, so 5, 8, 13, ... Right? Now, the classic way of solving this recursively is, of course, to write a function that recursive call to, say, the function, this is called fib for Fibonacci, of n minus 1 plus Fibonacci of n minus 2, right? That's the classic recursion that you see all the time in any programming language that supports recursion. This is usually the example that that people use. A quintessential example of why recursion is bad or can be bad. To see why it's bad, let's draw for Fibonacci of 5, or let's go with 6. All right, I want to keep 6 Fibonacci. Compute 0, 2, 3, 4, 5, 6. I want to keep this one right here. Well, to do that, you can make 2 recursive calls. One to Fibonacci of 6, so minus 1 is going to be 5, and I won't write out the full thing now. Otherwise, that would be too much writing. Then 5 makes a recursive call to 4 and 3. 4 makes a recursive call to 3 and 2. 2 and 1 over here, and then this is 1 and 0. And then finally, this is 1 and 0 as well. And then 3, you've got the same tree hanging off of this. 1 and 0. 4, basically, subtree over here and put it over here. 3, 2, 2, 1, 1, 0. And 1, 0, right? So immediately you see a lot of repeated computation, right? You can look at this subtree right here. This is repeated once, twice, thrice, 4, 5 times. Right? In fact, the number of times that a computation tree is repeated follows the Fibonacci sequence. The number of times that I'll invoke this function on Fibonacci of 0 to get that base case is actually going to be something like 13 or whatever. Might be off by 1, right? But it's going to correspond to the somewhere around the 6th Fibonacci number, right? So this is these are called overlapping subproblems. It's like tree overlaps with this tree. So what we want to do is we want to be able to identify those overlapping subproblems and avoid the extra work. Now, the way that I usually present this, say in CS1, is using memories. Once you compute the Fibonacci, the 4th Fibonacci number, you don't compute it again over here. You store it in a table, and then you look up that table and say, I already know what Fibonacci of 4 is. Here you go. It doesn't do this entire computation again. It does it once to get that initial answer, but then when you ask for it again over here, it doesn't compute the entire tree. It cuts out the tree. More rigorous approaching problems like this and identifying how you can do it from, instead of down, you're going from the top. Builds a solution from the bottom up. You're filling out a table. Example. I want to look at another example and to show you how you approach these things. Okay. So here's our old friend n choose k. Right? These are usually known as the binomial coefficients, because if you look at the binomial distribution or binomial theorem or whatever, all the coefficients to, like if you take a binomial, right, a polynomial in 2 values, and then you raise it to n, and then you expand it out, what does it look like? Well, you've got all these coefficients that are all of this form. N choose k for this being n, and then k running from 0, 1, 2, 3, all the way up to n. Okay? In fact, we've got plenty of time. Let's go ahead and look at it. What does it look like for, say, 3? Well, this is x plus y times x plus y squared. Right? So let's go ahead and figure this one out, and then we'll distribute x plus y. What does it look like? X squared plus 2xy plus y squared, right? Those are coefficients. I look at it from perspective of 2. 2 choose 0 is 1. 2 choose 1 is 2. 2 choose 2 is 1 again. Right? Let's look at it when I distribute this. Well, I get x cubed. I then get 2x squared y plus xy squared. Now I'll distribute the y, and I get x squared y plus 2xy squared plus y cubed. And now there are several repeated terms here. Let's go ahead and collect them. X cubed plus, I've got another term over here, so this is actually 3x squared y. And then this term matches with this term. This is 3x y squared plus y cubed. 3, 1. Corresponds to 3, 2, 0. Right? There's my first coefficient. 3, choose 1. How many of the ways are there of choosing one element? And then 3, choose 2. How many ways are there of excluding one element? Right? Yeah, got that coefficient. And then this one corresponds to choosing everything. Right? So these are the binomial coefficients. They're the coefficients of a binomial polynomial to a power of n. Okay? The number of ways of choosing k elements from a set of size n. So the usual way of doing this is n choose k. Does anybody remember the formula? N factorial over n minus k factorial. K factorial, right? Now, if you look really hard on this, you'll see that, well, if I actually wanted to compute this, I would have to perform multiplications and one division. All right? Well, let's not worry about that one division because no matter what, it's just one division. How many multiplications would you actually have to perform here? Well, how many are up here to compute the numerator? N minus 1, but you get away with 1. Why? When you get down to the last one times 1, don't do that, right? So it's actually n minus 2 on the top. What about this? N minus k factorial. Wait a second. Maybe we could get away with some not having to do a lot of these. Because a lot of these, these higher order terms, or sorry, these lower order terms are going to cancel out entirely, right? So if you count the number up here, take out the number down here that you're dividing by, so that you don't have to compute a big multiplication and a big multiplication and divide them. Just compute a small multiplication, no multiplications down here, and then you only have to divide over here. So it's going to actually be something like, and I'll let you do the work since I did the work on my own. It's only going to be about n minus 3 multiplications. Right? When you get down to it, because a lot of these will cancel out, and then a lot of these will add back in, and so you're only left with about order n multiplications. Now, strictly speaking, from an endpoint, then you know the size is the number of bits to represent n. So this is actually going to be, technical standpoint, this is going to be exponential. Is there a better way of doing this? A guy came along by the name of Pascal, Blaise Pascal, and came up with the following identity, where you don't have to do any multiplications at all. N choose k can be computed recursively, or divide and conquerly, right? Plus, so by computing n minus 1, choose k minus 1, and then n minus 1, choose k. Right? And he also identified two, or a couple of, a series of base cases here. If you have a set of size n, and you choose 0 of them, how many ways are there of doing that? A dozen students in this class right now. How many ways are there of choosing none of you? One way. Just don't choose anybody, right? So there's only one way of doing that. Likewise, if I want to choose all of you, how many ways are there of doing that? Also just one. Just choose everybody, right? That goes back to the binomial coefficients over here. 1, 1 on the side. 3, choose 0, 3, choose 3. Always going to be 1 on the endpoints of your binomial coefficients. Okay? Pascal, you can go ahead and do this. To do is a bunch of addition, right? I'll return binomial of n minus 1 comma k minus 1 plus there's my proposed solution. What do you think it's going to look like if I drew this? Let's go. Giant tree, where there's a lot of repeat. So at this point, I'm going to go ahead and, this is the second time I'm ever going to do this. Switch over to my actual computer over here. Is it up there? Nope, not yet. Come on. Is it up there now? Nope. There we go. Okay. So I've got a C program here that does exactly what I just described. Let's go ahead and look at it. So I've got several examples here. I called it choose instead of binomial, but the entire program is called binomial exercises. So let's go ahead and take a look at choose without any memoization here. Here we go. Here we go. So I've got some additional things here. For example, I'm going to count up the number of times I actually call this function. So it is recursive, and I'm going to call this function multiple times. I want to know how many times did you end up calling this function. And I've got some edge cases here to get, if you call it on negative values, it's not defined, so we'll exit on you. Otherwise, if k is 0, then we return 1. If k is greater, if you're trying to choose more things than there are to choose things from, like you're trying to choose 20 elements from a set of size 10, then that's invalid. I'll return 0. Right? Otherwise, if k is 1, then I return n. That's a different. That's a different base case than I had before, but it still works. Right? Otherwise, I make those calls to n minus 1k, and then I've reversed them here, but that's okay. All right, so let's go ahead and compile this and run this. I need to remind myself of something really quick. Okay, good. So GCC binomial exercises, and we'll run it. Okay. This will run, don't worry. And I'd ask you how long you think it's going to run, but it should be getting done. There we go. All right. I ran it for 37, choose 12. The reason I ran it on those numbers is because that's the maximum value that will be expressed by, I think I've got this represented as a long, which is a 64-bit 2's complement integer. But look at the number of calls there. That is correct. It made 1.7 billion function calls. Right? The recursion isn't that deep. The recursion is at most 37 levels deep, but the wide. Now what I'm going to do, I'm going to give it another argument here to use memoization instead. Right? And when I do that, did I have to wait 20 seconds? Nope. I get the same answer, but how many function calls are there now? Only 573. And the way that I did this was, instead of calling, say, 10 choose 5, how many times does that end up getting called? An exponential number of times. In this version, in the second version here, I only call it once. Once I've got that answer, I put that checks to see if it's in the table or not. In my table, it uses it to make the recursive call. It's still, however, a top-down solution. If you want to check it out here, that's what where choose with memoization recursive. All right, there we go. So there it is. Choose with memoization recursive. If you don't know C, that's fine. It's passing in all these values and these flags, an entire table of values, and then the original, then the n choose k that you actually want to use. Then it checks if the value has already been computed, simply return it. It's just checking this flag Tableau, this array, a 2x2 array, or a two-dimensional array, and then it's returning the value if it's already been computed. Otherwise, we're forced to compute it via recursion. So we'll recursively do it for n minus 1, k, choose k, n minus 1, k minus 1, choose k minus 1, using Pascal's identity, passing everything through, and then once we've got our value here, we save it off in our table, and we set this flag value to say, yes, it's been computed. So that the next time you try to do it, it takes care of it for you. Right? That's memoization, but it's the difference I want to look at, and I'm going to switch back now. The difference between just simple memoization and dynamic programming is, let's go back, is that you don't have any top-down solution at all. You start from the bottom and you fill out the table of values rather than using recursion. Okay? So I'm going to here. Okay? To this idea. And I want to make sure that I'm making my table look nice. What we'll do here is we'll have we'll run 0, 1, 2, 3, ... k minus 1, and then k. And then we'll run n from 0, 1, 2, 3, 4, ... up to k. That'll match this k. And then ... and then n minus 1, k. Okay, still on. But these are going to correspond to values, and whatever the row is, choose whatever the column is, k. And this is the one that I'm ultimately interested in. Okay? Identity. We can go and we can. Let's look at the base cases first. And choose 0 is always going to be 1. Where is that in this table right here? I'm going n, choose k, so if k is 0, in other words, this column right here, all of these column values, are going to be what? 1. ... Right? All of those column values are 1. What about the second base case? When n is equal to k, well, 0 is 1, 1, they're equal, 1. 4, equal, all the way up to kk, and they're all equal. Right? So, unfortunately, but you get the idea. All of these on the diagonal are going to be 1s. All of these in the first column are going to be 1s. Right? Now, from the other perspective of Pascal's identity here, how do I compute n, choose k, using this identity? Where is this first one? N minus 1, choose k minus 1. Where minus 1? Going to be one row up and one column over. So n minus 1, choose k minus 1 are going to be right here. Right? N minus 1, choose k. So it's just you want to look at any entry here, and you want to compute that entry. All you need to do is look up 1 and look up over 1, over left 1 and up 1, these two column values, or at these two, and you get your answer for that cell. We can fill some of these in. This will be 2, 3, 3. These are the ones that we just computed. Here. This is what value is stored here? Well, it's 3 plus 1, which is 4. What value is here? 3 plus 3, which is 6. What value is here? 1 plus 3, which is 4. You can go ahead and fill us out. What is this thing? Table, right? case, they're all in it below here. Rather than using memoization and recursion from the top down, we need to figure out how to this table out. As long as I fill out, I'm going to be the last row and a nice little algorithm that has nothing to do with recursion. Here's how we can do it. First of all, let's take care of cases. Okay. So I need to take care of this base case. I'm just going to go ahead and take care of them in one for loop. I'm going to run I running from 0 to and I will C sub I 0. That's going to be running from 0 to n, and I'm looking at the column 0, I'm going to set them all to 1. And then I'm also going to set C sub I and C for choose. You could use binomial. I'll set that. You do need to be careful here because once you get over here, matter if you end up that you're not going to use, then that's okay. This is an initialization. These are the base cases. And in the notes, by the way, I do have more formal of this. All right. Now, to write, this one is really easy. All we need to do is go for a for loop here. The exact same thing as before. For I running from here. So we'll start go to and including n. We want to compute the last row right there. And then we'll go ahead and go for j running from. We'll start it at I because we already took care of that first column. Or we'll start it at 1, sorry. And then we'll go up to and excluding when equal to what did I have before? I minus 1. There we go. And all we do is set C sub ij equal to C sub I minus 1, okay, plus 1 right above and 1 over is going to be C sub I minus 1, j minus 1. Do you see any recursion at all? Nope. I'm just filling out a table. All I need to identify recursion, identify the table and in which I fill out. By the way, what's the efficiency here? now you can go ahead and check out the efficiency here. That we'll forget the initialization here, but we're doing one addition. So how many additions to compute n? N choose k, where k is bounded by n anyway. So this is going to run from, well, we're table, it's n by k. If k is less than or equal to n, then it's at most n squared. Two loops right here, okay? And now this is, again, it gets kind of hairy depending on how you define the input, but at least it looks polynomial, right? And for all intents and purposes. No multiplications, no divisions at all. You're taking advantage of Pascal's identity, doing it in a manner that doesn't repeat anything, because the entire table, there are no repeated values in this table. But also, you're avoiding recursion. You're taking care of all. But it can lead to efficient solutions because of the abuse of the call stack. We took care of that by throwing out recursion. Repeated computation, we took care of that by designing the table so that we're not reusing values and not repeating values. Okay? All right, that's our motivating example. Let's identify, so there are a couple ways that you can, how this is done. The one that I kind of like, it falls a little bit short. It's called the FAST method. And it's basically just outlining your approach to each one of these problems. First, the first solution. All right, this is an acronym, so FAST, F-A-S-T. The first solution is basically that you identify a divide and conquer approach, a solution, right? And basically you identify base cases, you identify the division, or in the divide and conquer strategy, or subcalls, or the recursion. And if you remember in our process that we just now, we just used his identity. A stands for analyze a solution. That is, you find an optimal substructure. Another way that you can do that is by identifying overlapping sub-solutions. Right? We did that with Fibonacci. We realized that Fibonacci, calling Fibonacci of n minus 1, actually called Fibonacci of n minus 2 twice. In other words, this solution could have been reused for the other solution. They overlapped, right? Those computation trees, they overlapped because they were repeated. S stands for sub-problem identification, where you memwise, I don't know why people call it memwise. There's a better word for it, cache. Cache. If you cache things, basically you're saving them off for other, for future reference, right? Then you turn around, and that's the T in FAST. You basically transform it from a top-down solution into a bottom-up solution. Bottom-up. So that's the FAST acronym, and I think it falls short because the person that designed it, I think, was just trying to develop an acronym for it. Well, this kind of does that, and this kind of does. Oh, it spells FAST. Great. Work. Give you a little bit well, it's a less, it doesn't have that, but it's at least a little bit more straightforward. One is you define or derive a recurrence. And in the context of Pascal's identity, he did it for us. Right? Two is you design a table. Or if you want to be fancy about it, a tableau. Right? Have a base. Then you're going to identify dependencies. Right? These two other cells, because that's you can devise a strategy for filling that table. But then, I don't want to skip this, you identify the final cell. Right? Which one are you actually interested in? You're not interested in that we built here. Here we go. I don't care about but of these, then you can go ahead and program a loop to fill out the table, consistent with these up here. You go through and you identify. Tells you what direction I need to plot that table and terminate the condition. Okay. A brand new problem that we haven't seen before. Okay. This brand new problem is called optimal binary search trees, or OBSTs. Optimal binary search trees. And optimal binary search trees are, the goal is a little bit different. The goal is to minimize the average number of key comparisons for any search. The goal is not necessarily to have a balanced tree, not necessarily a balanced tree. Okay. Now, here to understand it completely, but basically, the is we're going to insert or dynamic. We're not continuing. It's basically a collisions, and we'd have to resolve those collisions. And if we don't use things, then we would have to set bits on everything to say that it might not even be a collision anymore, but the thing that you're looking for is somewhere else entirely. Right? You can, if you know that here's 100 things that I need to store in a hash table. Let's go ahead and compute a perfect hash function. In other words, there are going to be 0 collisions. As long as I'm not inserting new stuff and deleting stuff, then that's as good as it gets, right? Because I have a hash table that is exactly size 100. I've got a hash function with 0 collisions. Everything gets mapped somewhere and only one place. Right? You can derive perfect, but only if your data is static. Okay? We're going to look at that from the perspective of binary search trees. And another condition here is that you know the search probabilities of every key, or at least you have a very good estimate. Okay, so this is a very, very particular application that you would want to use something like this. Okay, as an example, let me go ahead and give you 3 keys, A, B, and C. And let's go ahead and assume that we know the probability of searching keys 0.6, 0.3, and 0.1. Right? The interpretation here is that 60% of the time A is searched. Only 10% of the time is C searched. And 30% of the time, B is searched. Right? And you can kind of imagine that this is a real scenario, right? I don't know. Something that's more popular than something else. I don't know. The classic example I like to use is, now I even forget the name of it. It's a Celtic game, kind of like field hockey. I don't remember what it's called, though. It starts with an S, I think. Anyway, let's use another sport. Football, NFL football, is way more popular than, say, I don't know, tennis, right? Not to say that tennis is unpopular, but certainly NFL football is way more popular. In other words, if you go to Google, people are probably searching for NFL terms way more than they are searching for tennis terms. Right? Did anybody look that up? I think it's called, what is it called? It's like Celtic field hockey. Shinting, thank you. It's called shinting, or shinty, right? Shinty. I don't know if they call them shinters or whatever, but it's shinty. I only mention it because one night, a long time ago on ESPN3 or something, late at night, they were broadcasting a shinty game, and I was like, what the hell is this? Actually broadcasting it. So shinty, of course, nobody's searching for, very, very few people are searching for that. So maybe shinty is searched for 10% of the time, while NFL football is searched for 60% of the time. And then, I don't know, NCAA football is searched for 30% of the time, right? So let's look at these keys, and these keys are A is less than B is less than C, right? Assume that. So let's look at a couple of binary search trees. One binary search tree that we could have is a perfectly balanced binary search tree of depth 1, A, B, and C here. Right? So under this scenario, if I were to search for B, then search for, dot. If I were to search for B, how many comparisons would I need to make? Well, it's right at the root, so I would only need to make one comparison for that. If I searched for A, how many comparisons would I need to make? I would start at B, that's not it, it's less, go left, that's it, so 2 comparisons for A. And likewise, there are going to be 2 comparisons for C. You compare it to B, see that it's not the thing that you're looking for, so go right and right there, right? Now, when you take into account a weighted average number of comparisons, this is very similar to what we did with this is for 60%. tree. Right? Can we do better? Let's look at another unbalanced binary search tree. What if I unbalanced it completely to the, say, left? That's even worse, right? Before we only had one. So this one is, yeah, better. Wait. 1, 2, and 3. But with a distribution of 0.6, 0.3, and 0.1, what do I have now? 0.6 plus 0.6 plus 0.3 is going to be 1.5. Example, how many 3 keys say 100 keys, how many solutions would you have to? That the number of different binary search trees with n keys corresponds to the Catalan numbers, which is C sub n, and it's actually n plus 1. That's okay though. 1 over n plus 1, 2n, choose n, which is going to be exponential. I think I've got 4 to the n and then something on below 1.5. I think that you can get that using Stirling's approximation. Right? So are we going to be able to do this from an exhaustive point of view? 100 keys, which is absurdly small. You're going to be able to do 4 to the 100 possibilities run through them all? Nope. That's okay because many of those things will be suboptimal and a lot of them will be overlapping, right? If you put a bunch of, if you put keys 1 through 10 in the left subtree, you've got the key 11 as your root, and then you put all the other keys over here, a lot of those are going to have overlapping subsolutions because you divide it a different way over here, but you leave everything over here the same. Well, you don't have to recompute that solution over there, just like the binomial coefficients. Okay. So, questions on this? Again, we want to minimize the total number of key comparisons. It requires of how much, or at least an estimate on the probability distribution of all your keys. Okay. So let's method. You need to think about how we can divide and conquer from a high level. So given keys K1, K2, to Kn. Here's my first question. So my first solution, F and fast. Question, what is the best node to use as the root? Right? Is it the first one and then skew everything to the right? Or is it the second one? Or is it the third one? Or is it the fourth one? Or is it the last one? Right? Let's say that the answer, let's keep it general, let's say that the answer is K sub L. Right? What does our tree look like then? K sub L is our root, and then we've got a left subtree here, and we've got our right subtree here. In other words, you choose one of K1 is less than K2, ... is less than Kn. So it belongs over K1 through K of L minus 1. And what's over here in this right subtree? K sub L plus 1, ... through to the end, K sub N. Okay? That's kind of the first solution. Let's think about the recursion, and suppose that I don't have all of these keys. I recurse on the left, and I recurse on the right, so I only have a side. Thinking about it more generally means that you have a split. Given Ki through Kj, we want to find the best root K sub L so that it looks more like this. Ki through K sub L minus 1 and K L plus 1 through K sub J. Okay? That's the recursion that this picture really looks like. Oh, let's define. Now this is still part of the F, I guess, of FAST. We need to define our recursion. Define C sub ij to be the optimal number of comparisons in an optimal binary search tree, OBST, with keys Ki through Kj. Right? So in other words, this is the beginning of my table right here. Right? Now, I need to find the best split. Well, I could have the best split at I, or I plus 1, or I plus 2, or I plus 3, or j. Right? So I need to consider all of those potential splits. C sub ij is going to be the minimum among I through j of, now here's where my optimal substructure comes in. Well, if I've got a value, that's I through L minus 1. So, and then you have to take into account over here the keys L plus 1 through J. Oh, and I wrote my curly bracket here too big. Sorry. But that's the minimum. I'm running L from I plus 1, I plus 2 to J. And I'm taking the minimum here. I also need to take into account that suppose that this tree was of depth D1, and this tree was of depth D2. By combining them, I've made now a tree deeper. Meaning, if it were, say, to find any key over here, now there are D plus here, one step deeper. So S. So this right here is the fact that the new tree is deeper, and there's keys. K, I through K, J. That's why I run it from I up to J. I just needed a new for that. This here is the probability of key K sub S. All right? If you take the minimum over here, you really only need to compute this one. That's our substructure property. Yeah, let's go with this. Let's think about some base cases here. How much does it cost to search an empty tree? Does it cost you any comparisons? 0. So, when does that happen? Remember, C sub ij it is going to be K sub I through K sub j. So when do you have an empty tree? When? You don't have anything here, right? Say that it's K3, K4, and K5. That's not an empty tree. K3 to K3, that's not an empty tree either. That's another base case, though, because you do have this one key here. But what happens when you have no keys? Say 4 and then 3. Right? Key 4 through key 3, does that make any sense? It's not in order, so no. So I and I minus 1 has a cost of 0. Okay? Now what happens? This is an empty tree, cost of 0. What happens when we just have one node, like this over here, K3? What's the cost there? 1. But now remember, the real average cost is going to be 1 times the probability of it. So 1 times the probability of K sub I, which of course is just, get rid of that 1, is the probability of K sub I. This is a single node tree. Okay? So, applied our recursion. Which one interested in? So what's the final cell? The original problem that we're interested in is, that's not it. Given keys K1 through Kn, what tree are we looking for? C sub 1n. That's the point. It's going to be approximately an n by n table. Let's go ahead and go with I and j. I is going to run from 1, 2, 3, dot, 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 n and n plus 1. And this is just a technicality. I'll show you why here in a second. And oops, j is going to run from 0, 1, 2, 3, dot, 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 up to n. So here's my table. Again, what am I interested in here? First of all, what are some of the base cases? C sub I and I minus 1. So where am I looking at here? Where is that going to be 0? 1 and 0. Keys 1 through 0, is that defined? Nope. Keys 2 through 1, is that defined? Nope. Keys 3 through 2, is that defined? No. Key 1 and through 1, that's defined. What is it? That's one of my base cases. That's the probability of key 1. 2 to 2, that's the probability of key 2. 3 to 3, that's the probability of key 3. Right? Dot, dot, dot. So when I've got n and n plus 1 and n over here, that's going to be the other base case. And then right above that, that's going to be probability of key n. Right? So there are my base cases, right there, those two diagonals. Okay? Now, which is the This is the one that I want. How do I get there? Again, I can't draw it better than I've already drawn it in the text. So, okay, come on. I'm glad that if I hold it down, it goes really quick. There we go. That's good enough. But focus. There you go. To do that, I have to consider split at C sub I, C sub I plus 1, I plus 2, I plus 3, all to C sub j. Each one of those things, think about it, if I've got 4 keys here, I could promote this one up, and then these 3 keys go down here, and no keys are over here. Or I could promote up the middle one, and there's 1 key over here and 2 keys over here. Or I could promote this one up, 2 keys over here, 1 key over here. Or this one, and then 3 keys over here, and no keys over here. Right? Each one of the 2 values. Here we go. Split that corresponds to this value, and then over here it corresponds to this value. Right? Those 2 things together, and then sum up that probability. For L and I. Because then I plus 1, j. The second split that I consider is at I plus 1, which will correspond to this, and then the other value is right over here. Then the third split corresponds to this value over here. So in other words, the xth split, x value on this row is going to correspond to the xth value in this column over here. So what does that suggest? That I up to this point, I need this entire column up to this point in order to do it. In other words, I need to fill it out diagonally. Right? And I need to do so starting at the bottom left, going all the way up to the top right. Because if I don't, these now, fortunately, I already did it for you. So let's go ahead. Write this code for this. And for this, I'm going to have to go, all the way back. Switch over to a smaller pen so that it fits. Input here is going to be a set of keys, K1 through Kn. You're going to assume that the order that they're given in is already the order that should be there, and a probability distribution, P, on these keys. And our output will be an optimal binary search tree tableau. All right. We're actually going to output 2 things because eventually we want to build this tree. And so we're going to have to keep track of additional information, just like Floyd-Varshall's and Dijkstra's algorithm. We had to keep track of what gave us that solution. We're going to keep track of that with respect to optimal binary search tree. So here's our initialization for I running from 1 up to n. We're going to take care of those base cases. I and I minus 1 will be 0 because that's an empty tree. C sub I, a single node, is simply going to be the probability of the ith key. Right? Again, that's one of the other base cases. And this R sub I, I'll explain in a bit, That's actually going to be a root table. That's the thing that we're going to need to actually build the tree. We're going to keep track of what key values were the best for split for that tree, so that we can actually build it after we do all this stuff. There's one that's not taken care of by that loop. I just wanted a clean loop. You could, instead of having 3 loops. So that's that last one. That's that one right there. Right? It just doesn't fit into the loop because the other 2 loops have already fallen off the face of that table. Okay. Now again, here's the complicated part. I could assign it. In fact, it is assigned in other courses I've seen of figure out the loop to accomplish that diagonal structure, bottom left to top right. Here it is. Right. So this is the dth diagonal row. That's all I'm doing here. And then for I running from 1 up to n minus d, right? Then I'm going to do the following. So I need to compute j. J is simply going to be d plus I. This is the dth diagonal row with an I offset, I running from 1 up to n minus d. So basically, again, so I've got my I, I've got my j. I'll go ahead and set a minimum. I'll go ahead and use inf, or infinity, right? Because any other solution is going to be better than that, more optimal. Now for L, running from I up to j, this is where I'm going to capture this notion right here. What's the best split? What is the minimum value among all of these? Okay. So I'll compute Q, and Q doesn't stand for anything in particular. I up to L minus 1 plus C sub L plus 1 J. That's that thing right there. And I will compute if Q is less than min, then I need to update a few things. And unfortunately, I'm running out of room here. You know what? I'll go to the second page. If I'll update my min to be Q. And then I will also update my root table. Roots of ij, excuse me, should be L. L is the value that gave me this better value, Q, and so I want to keep track of it. All right. At the end of this inner for loop, we'll go ahead and put in the final entry of C sub ij to be the minimum value that was found in this loop up here, plus that summation value, I, or S is equal to I up to j of P sub k sub S. Right. Remember that this summation was separate from the minimum value. That's why I'm only computing it once at the end. Right? You don't need to compute it on every single iteration of this for loop. Just compute, and it doesn't even, it's going to be the same min plus 5 and a plus 5. You can take out that plus 5 and compare min and a, right? So that's why I'm only computing it at the end. And that's it. There's all your for loops. That fills out the entire tableau. You output C sub 1n and this root table, right? Now, we're not going to have tomorrow, but of the time I did run through an actual example, the entire thing, because it gets somewhat tedious. But when we come back tomorrow, I'll show you how to actually build. So for now, we're only going to concern ourselves with the actual comparison values. Okay. So here's the input. Where's my input? Here's my input. My input is going to be 5 keys, A, B, C, D, and E, with the following probabilities. Again, the interpretation here is that 21.3% of the time A is searched for, only 2% of the time is B searched for, 54.7% of the time C is searched for, 10% of the time D is searched for, and 12% of the time E is searched for. Okay? That's my input value. Now let's go ahead and look at the table here. So let me pull the table back that we designed earlier. Here we go. So n here is going to be 5. So I need a table that is 1 to 6. And it's going to be pretty bit large here. And then j is going to run from 0 up to n, which is, I don't need 0 here. So let me go ahead and just put I right here and j over here. It runs from 1 up to n plus 1. And then j is going to run from 0, 1, 2, 3, 4, and 5. Right? And again, the one that we're interested in here the most is this one right here. And then you can draw cells all. I will set up the table. Remember that these are all going to be the base cases. That if I just go down the diagonal here, well, it's undefined of keys 1 through 0 because there is not even a 0 key here. So 0, 0, 0, 0, 0, and 0. Right? These are going to be all the probabilities. 0.213, 0.020, 0.547, 0.100, and 0.120. The initialization would set up all of those, right? And it would go in the exact order that I did it in. It would go top left to bottom right diagonally. Okay? Now, pull out my recurrence definition over here. I is 1, j is 1, so we need to run up to 2. So the way that I'm going to present this is going to be the minimum of 1 up to 2 of the following. So I'm going to go ahead and put both of these in here. L is 1 or L is 2. If you just have keys, if you have just keys A and B, you can either put A at the top and B as a right child, or you can put B at the top and A as the left child. Those are the only two options. By L being 1, split it at 1 and put B as the right child, or split it at 2 and put A as the left child. Okay? This is the value of I. I in this case is 1, L minus 1 is 0, plus C sub L plus 1 is 1, so 2, J, which is 2. And so all that you have to do is this, if you look up C sub 1, 0, well, that's going to be 0, because the left subtree is empty. You put A at the top, B goes to the right, well, there's nothing to put into the left tree. 2, 2 is going to refer to the fact that B is now over on the right subtree, so it's going to be 0.020. Right? Now this one is going to be C sub I, L minus 1, C sub I is 1, L minus 1, L in this case is 2 though, so it's 1, 1. That corresponds to putting A at the top, in the left subtree, And then B, or the right subtree, we have a cost of, this is going to be L plus 1, which is 3, and J, which is 2. If you look these up, putting A into the left subtree will cost you 2.13 plus, well, now with an empty right subtree, 3, 2, that's going to be 0. So which one is the minimum? This one wins out. And so this tells us that A should be the root of the subtree consisting of these two keys. And so what we do is we come up here, 2, and we put in 0.20. Okay? Only two values here. 1.033, 0.587, 0.787, 0.747, what else? 1.233, 1.127, 1.087, and 0.320. Okay? Cell over here. For that, am I running? But that's over here. C sub 1, 5. It's going to be the minimum of all, considering L to be split 1 up to 5. So there are going to be a lot of possibilities here. Not a lot of possibilities, only 5 possibilities. A polynomial number of possibilities, where your split is at 1, your split is at 2, 3, 4, or 5. And again, this is the final answer. You're asking, well, what's the best split between all 5 of my keys up here, A through E? But this final answer is only possible by you having filled out this table to get to this point. Okay? So, here we go. I'll go ahead and leave it up here, and we'll then we can reference it. So an I is going to be 1, so C sub 1, and then L minus 1, in this case L 1, so 0. C sub 1, 1. C sub 1, 2. C sub 1, 3. C sub 1, 4. Plus. And then what are these values? This is L plus 1, so C sub 2. And then J is fixed to be 5. C sub 3, 5. C sub 4, 5. C sub 5, 5. And C sub 5, 6. Okay? And again, all of those are just table lookups. Here, 1, 0 is going to be 0. 2, 5 is going to be 1.127. 1, 1 is going to be 0.213. And then 3, 5 is 1087. Add those up. 4, 5 is going to be, 1, 2 should be 2. Oh, you know what? Did I screw up? 1, 1. No, I'm screwing up here. 2, 0. There we go. 1, 2. And then 4, 5 is 0.320. 1, 3 is 1.033. 5, 5 is 120. And then 1 to 4, this is 1.233. And then 5 to 6, did I get that wrong? 6, 5, thank you. 5 is all the way there, and then that's 0. All right? Take out your calculators if you want. Did I actually do this? Well, whatever. 1.573. And that corresponds to 3, this one right here. Right? Now, why isn't it 1.573 here? Remember, we have that summation, right, of of I running from 1 up to 5 of P sub K S, right? And so we've got some extra values up here. And hopefully I did this correct, but I do know that this one is definitely correct right here. So the final answer is that you should split it at K equals 3. In other words, this one corresponds to C, and then over in the left subtree, we have A through B, and we have to answer the question of how do we split it there. And then on the right side, we have D through E. And then we've got the same question of how do you split it over here. Sorry, there we go. If you want to look at it from a different perspective, this one, where an L is equal to 1, that means that you're splitting it at A. And then there's no left subtree, it's empty. And in the right subtree, you have B through E. All right? At another end of the extreme, L equals 4. That is you splitting it at D, and then over here you've got E. Well, I don't even want to make that into its own tree because there's only one element over there. But over here it's A through C. And then you've got the other that. What is the optimal substructure there? Fortunately, you already did it up here. How do you split from A to B? 1 to 2? Well, that's the best split right there. And presumably you've been keeping track of these L's so that you can rebuild the tree. That's what we'll do tomorrow. We'll show you how you can rebuild the tree, and then we'll write an algorithm to do it after we've gotten this filled out, along with the root table.